Okay, so we'll go ahead and get started. I know people are still joining, but good morning, good afternoon, everyone. Thank you so much for joining us today and welcome to the Hive Think Tank webinar series. So my name is Olivia. I'm the operations manager at the Hive in Silicon Valley, and we're super excited to have everyone join us and hear from our expert panel speakers from Princeton University and Alistair. So with that being said, I'm going to quickly go over some of today's best practices for the webinar and explain what the Hive Think Tank does. And then I'll go ahead and pass it over to Ravi, who is the Hive's founder and managing director. So we do love questions. So we'd love for the audience to use the Q&A button and not the general chat box at the bottom of your screen to ask our presenters questions at the end and also throughout the panel discussion. And then this event is also being recorded, so it'll be available on our Hive's YouTube channel later on, which I'll share at the end of the events. So the Hive Think Tank is an ecosystem of thought leaders, corporations, and entrepreneurs. We're an events and content platform with a focus on AI, enterprise, security, sustainability, health tech, and so much more. So we do host events almost every other week on cutting edge topics and technology and business. So I would highly encourage everyone to join our meetup group and newsletter just to stay up to date on some of our upcoming events. And Ravi will speak more about that shortly. And I'll also link the meetup group in the chat below. So lastly, I do want to thank our sponsors, Avanta Ventures and Gamuda, for their support. And if anyone is interested in getting involved in the Hive Think Tank, feel free to reach out to me directly. And then make sure to follow us on LinkedIn and Twitter. So with that being said, I'll go ahead and pass over to Ravi, our managing director, to talk more about the Hive and introduce our speakers and some of our upcoming events.
Great. Thank you, Olivia. And if you can go to the next slide, great. So just briefly to introduce the Hive is an early stage venture capital fund. We collaborate actively with partners. We are now in our fourth fund. We were started in 2012, and we have a global presence. So in addition to the US, we also have presence in Brazil, Southeast Asia, India, and very soon in Europe. Key focus for us is data and AI. And in addition to kind of AI and data platforms, we focus a lot on enterprise and cybersecurity solutions. Next slide, please. We have a whole series of events that the Hive Think Tank is hosting on generative AI. There is a second series that I urge you to keep an eye open for, which is around the future of work. But today on the generative AI events, we've recently done an event with Alistair moderating on Databricks open source LLM called Dolly. Today, we'll talk more about today's event later, but we have a whole series of other events coming up. Next, Olivia. So the next event in the end of July is a CIO perspective on generative AI. One of the opportunities and challenges that CIOs face is that people are not waiting to get permission. They have started embracing ChatGPT and other tools to help with their work. They've been uploading some of their the corporate information. And so the CIOs want to try to put their arms around it, but also look for whether it's sales or marketing or customer support, or IT, where can generative AI deliver sort of immediate results. The next slide, please. We next host an event with ServiceNow, NVIDIA, and one of their mutual customers, which is Uber. And the focus of this event is on customer service and customer support and how that leverages generative AI. That's on August 3rd. Next slide, please. Enterprise software vendors are beginning to embed LLMs and other or kind of put wrappers around ChatGPT and deliver services. Some of you have probably seen the recent announcements that Salesforce made, and SAP has also been doing a lot of work in this area. Our good friends at Rockset have some very interesting innovation in the space. So I'll be hosting an event and moderating a talk on this. Next slide, please. And so coming to today's event, I'm incredibly excited to be hosting today's event with Karthik Narasimhan, who's a faculty member in computer science, along with Ellen Zong. As many of you know, Karthik was also co-author of the original GPT paper when he was at OpenAI. Alistair is a good friend of the Hive, an advisor of the Hive. For many, many years, was the chairperson of the Strata Conference, O'Reilly Strata Conference. He has written a number of books. Probably the best known one is Lean Analytics. And so with that, I'd like to hand it over to Alistair.
Thanks, Ravi. Always great to be here, and I love the conversations we've been able to have. This is an interesting topic because the very title of the topic is kind of strange. So what I want to dig into as we get started is making some sense of those words. And it's great to have Karthik and Ellen here because I think they bring some very interesting perspectives. The title, non-language use of large language models seems like a contradiction. So Karthik and Ellen, before we get started too much, I'm going to challenge you to kind of explain that a little more. But before we get into that, Karthik and then Ellen, why don't you briefly explain sort of what you work on these days and where your area of focus and research is right now. Karthik, why don't you go first?
Sure. Hi, everyone. I'm Karthik Narasimhan. Our lab's research here focuses broadly on many things around natural language processing, but like one recent area of focus has been around the idea of language agents. So you can think of these as systems that understand language and use it for decision making, much like humans, right? So if you think about why language exists, humans use it to communicate with each other and also to store knowledge in various forms that help them make decisions, sort of share knowledge with each other and so on. So how can you get machines to do the same thing? Read text, understand text, generate text, but do that all in the context of some downstream task or downstream decision making that they're aiming to accomplish. So that's the high level idea.
All right, and Ellen?
Hi, yeah, thanks for having me. So I'm interested very broadly in AI for science, which is, a very hilarious, broad category of things, but specifically our group works on machine learning for structural biology. So how do we kind of study the three-dimensional shape and structure of proteins and other biological molecules? Even more specifically, a lot of our focus is on a type of imaging data called cryo-electron microscopy. So how can we take pictures of these proteins and make sense of their three-dimensional shapes, maybe integrating other sources of information like, this language information about proteins and from biological data, and so on. And the ultimate goal is really to, discover new biology and push forward kind of our understanding of how the world works through computational techniques.
Awesome. So we're going to get into some of those applications first, but I should first of all remind all of the people who are here today, I'm going to be selfish and ask a bunch of questions because I have tons. But if you'd like to get some questions in too, you can click on that little Q&A button in the bottom, propose a question in there, and I'll make sure we have some time for those as we get through today's content. So as I was getting ready for this, I think everybody here knows I'm not a scientist, but I'm curious enough to ask questions about science. I want to talk about the fundamentals of using language models for non-language things. Machine learning obviously has been advancing for decades, but it took, I think, the last couple of years to really capture the interest of the public at large, because all of a sudden you had this user interface with zero learning curve. Like anyone can literally use it. It will even tell you how to use it. That takes text inputs and produces sensible responses or decent art. And then it kind of broke into the mainstream, right? So in that way, in that regard, large language models have helped us to understand a particular kind of machine learning pipeline. Like there are expert systems and there's other, there's diffusion models and stuff, but this very specific one, and Karthik, you just said it earlier, like why language exists. So before we get too deep into the technology here, can you expand a bit on like, is language a representation of thought?
Well, yeah, there's a whole debate in cognitive science about this, language as thought, but in some sense, it's a way of communicating information, right? So when we say language, I think most of us automatically assume human languages like English or, French, Hindi, things like that. But anything can be a language, right? Even programming languages are languages, right? Math is a language. There's more structured languages. Code is a language. They're more structured languages, whereas English is sort of like an unstructured language. But this sort of that sort of explains why you can, when we traditionally call language models, it sort of arose within the field of NLP, because NLP was looking at sort of getting machines to understand human languages, right? And so that's where the term language model came about. But if you really think about a broad definition for language, basically what you said is true, right? Like it's any form of any sort of form that allows you to communicate or allows you to store information.
Ellen, do you buy into that? Do you think language is thought?
Yeah, I definitely think there's something really nice about language in that it's this synthesis of information into some kind of representation that we can, move between entities. And so I think, I don't know if it's thought really, but I think language is particularly useful for, training these like top-down machine learning models, because they really efficiently represent kind of concepts.
So I remember, I tend to come down on the language as thought side, and I remember listening to, I think it was a National Geographic podcast, and I can't find it these days, which probably means I hallucinated it if I'm an LLM. But the author was saying that she was working with deaf mutes in Africa, and as a group, they would get together every day, and they had no language. And they would get together every day and they would mime out what happened during their day, but they would just reenact it. They wouldn't speculate. They wouldn't vary. There was no fiction. And she worked with them to teach them sign language. And one day, one of the students she was working with ran out of the room crying and didn't come back for like 3 days. And then on the 4th day, he returned and she continued to teach him sign language. And a year or two later, when he was more articulate, she asked him about the experience. And he said, I don't want to talk about it. I was an animal. I did not know how to think. And to me, that always seemed like, I really wish I could find it, because it seems like a really interesting sort of empirical language is thought, or at least the symbolic representation of the relationship between ideas. And so what got me thinking in preparing for this is that maybe from language, we extracted the blueprint of thinking, like what is of how to think about concepts. And now we're applying that blueprint to things other than words. Is that an accurate way of explaining what we're about to discuss?
Yeah, you can think of it in that way, right? Because just sort of like writing down things allows you to think in a compositional manner. It's also the types of thinking that it can enable, right? Like if I asked you to, I don't know, solve a math problem or something like that, some people just like to use some sort of a scratch pad, write it down. Maybe it's more some way of like having a short-term memory that allows you to think in a compositional manner, break down the problem into a hierarchical structure, and then, do this multi-step reasoning. So you are right. I mean, it does allow us to do certain kinds of thinking, perhaps easier. I'm not sure whether like you wouldn't be able to do it at all without language. That's the jury's still out there, but it certainly helps.
Sure. So I can already see people in the Q&A wondering if this is just about my pet theories on language. So we're going to get into some more deep technical things. What I'm trying to do here is to tease apart the concept of large language models, which is pour in some text, get out some text, and what needs to happen when we apply these sort of LMs to other things, right? So if you had to go back, this is the last question I'll ask on theory here. If you had to go back in time and change the name of large language models to something else, what would you call them so that we didn't have this confusion about them only being for words?
Karthik, do you have an idea?
Like I said, I think like the definition of language should just be broadened, and I think it's fine to call them language models as long as they're dealing with text or characters. I know, folks at Stanford have a name called foundation models that they've sort of had, but yeah.
It's
All
funny
right.
because I don't really think about these things in this like cognitive science framework or in this like abstract notion. Like when I'm doing research using these like types of models, it's very much just like, okay, can we get into the weeds of like, does this model work? Is it processing the data correctly? Like, how do we actually make these things more powerful? So it's nice to have this conversation and be reminded about kind of the LLM craze and like everything that's going on, I think, in Silicon Valley these days. But in my mind, the way that I think about these models is really just like big useful models, maybe on sequential data. So it's kind of a cheeky answer, but I don't know. That's kind of the way, from my perspective, that I've been approaching like this class of research or in this research directions.
So can you maybe take a minute and explain, we touched on three sort of, I think, key concepts for this stuff to understand these generative models, temperature, attention, and perplexity. Karthik, why don't you take a stab at explaining perplexity for us?
Right. So, I mean, this is, again, comes from the decades-long theories in NLP, right? So perplexity, the word itself means confusion, and you can basically think of perplexity of a language model as a measure of how confused it would be about the next output, the next token it's trying to output, right? So a language model is basically given some context and it's trying to predict the next token. And you can, it's a number, basically, if the number is 10, it means the language model is confused between 10 choices it thinks are right tokens to fill in the next gap. And language inherently has perplexity, right? You cannot get it down to 1 or 0. And so it's a very nice metric that also has information theory backing it, that allows us to evaluate and compare different language models.
Okay, and what about temperature and attention? Ellen, do you want to take a stab at those?
Sure. I mean, attention, I think, is one of the biggest advances in machine learning and computer science over the last 5 to 10 years, I guess 5 years. And it is, I guess I would describe the attention mechanism as a way of reasoning over kind of a sequence or a set of objects instead of going through things in a prescribed order, like sequentially, or with specific, like convolutional models. Here, we're explicitly letting the model decide what parts of the sequence to pay attention to. And so I think the original motivation for attention also had some design on like how we humans reason over text or textual information. But it's this kind of very elegant mechanism for letting the model decide what parts of a sentence to pay attention to.
So an example of that, if I said, Alistair opened the can of Coca-Cola, there's the can obviously relates to Coca-Cola and Alistair relates to opening and so on, as opposed to just the words that are next to like the.
Mm-hmm.
All right. How is that different if you're not looking at language? If I'm looking at a table of data, for example?
I think it has a very nice, I think it's just a very convenient kind of operation that's very flexible for different types of underlying biases or underlying kind of structure in the data. And I think that's why these transformer-based architectures have been very successful across many different types of data modalities. But, for other like very different types of data, it might still make sense to use convolutional neural networks because you just have this like translational invariance that you want that specific architecture. So I don't think there's like a general kind of, yes, this will apply across many kinds of different data, but I think the attention mechanism has been particularly useful for many kinds of human-related data modalities.
Okay, so last question before we dig into non-language models. There's this concept of temperature. And one of the key differences here is that we're talking about non-deterministic software versus deterministic software, where deterministic is I put data into a glass box, it processes it, and I check the output to see if it did what it was expected to. Whereas here we're talking about I put data into a black box and I look at the output to see what unexpected and clever things it did. And we really have like a second kind of software, but there's a knob called temperature that allows us to change that property of non-deterministic software. Karthik, do you want to talk a little bit about temperature?
Yeah, again, this is an artifact of the fact that, natural language inherently has different ways of completion, right? So the complexity is not one. And therefore, if you want the model to you want to sample from the model, that means, given the exact same context, you can have, many different completions depending on how long you want to complete it. And so this just provides us a way of having different samples from the model, like generating different samples from the model. And that's like, if you want to make it deterministic, you can set this sort of temperature parameter down to 0, and that sort of helps you get exactly the same sample every time. But it's more of a statistical thing that allows us to generate from the model.
Okay.
I think sorry. I was going to say, I think there's like a nice kind of physical intuition, which is like the actual temperature of a system controls kind of how chaotic it is or how the entropy of a system. So like it's just in like stat mech, where we're talking about a distribution over the configurations of any given system, the temperature controls kind of like how much you're in the like cooled low energy states. But if you have a very high temperature system, then you can like more efficiently explore lots of different configurations. And so there's like a physical meaning to some of these concepts in like other domains.
Sure. 0 Kelvin, there's not much that's going to get changed, right? So I'm glad we sort of did that background, and I apologize for some of the people who are watching who are like, yeah, I know what attention and perplexity and temperature are, but kind of wanted to get those as a level set, because now I want to talk about non-language models. So we have a system that can reason, and our definition for reasoning is like understand the relationship between ideas or concepts. And we have a bunch of data that's not language data. Let's say it's tabular data of some kind. How does the machine learning pipeline, the sort of ML ops, change in order to deal with things that aren't language and therefore can't use traditional attention models that we would have built for a large language model? Karthik, do you want to take a stab at that? Like, what do you need to engineer differently to look at tabular data, for example?
So just to make sure I get your question correct, so you're saying with an LLM, you want to manipulate tabular
If I
data?
want to make a machine learning model based on LMs,
yeah,
that is able to reason about tables instead of reasoning about text, how would I need to change what I've done?
Right. So the naive way would be, you can still make the table into a textual form, because it's, at the end of the day, it's just characters, right? And you can get the model to do some operations on it. And we already have evidence that models like GPT-4 are powerful enough that you can just feed in a table in some ASCII format and ask it questions, right? But more broadly, I think one way to use these models is to actually generate structured queries, right? So if you want to query a table, you can generate SQL or some kind of a code, that makes it more, it makes it more deterministic, but also probably more scalable, because once you write code, it's probably easy to apply it to different kinds of tabular data, different kinds of structured data that you want to extract information out of.
So what are the kinds of things that you can put in? You said anything that can be a sequence. Ellen, tell me about what people are doing in the life sciences field, either in cryo-electron microscopy or genetic information. What kinds of things are people putting into these models?
Yeah, so I think the most direct analogy from like natural language, large language models are protein language models, or kind of like these large language models trained on these databases of genomic sequences, genomic data, whether that's DNA, RNA, typically proteins, because it's a little bit more, it's a more expressive language, even though you can convert from the different forms. And they've been shown to be really powerful. So again, we have like these huge databases with billions of sequences, and like a traditional problem in computational biology and bioinformatics are just developing algorithms that can, process all of that string, like all of that string information. Now we can have that be ingested by a large scale, like attention-based model, and then that can already like compress a lot of useful information about the underlying kind of implementation of this genetic information.
So what can you do with that?
Yeah, there's like many different, I think one interesting thing is you can play around with designing new types of proteins. Perhaps you can, one kind of interesting parallel is that AlphaFold is this like machine learning model that can predict protein structures. And even though it's not officially like this large language model, the data that these models have been trained on are these like large databases of genomic sequences, as well as structure, like 3D structure information. And so one thing that's been really exciting is that you can take these models, train it on these large kind of rich corpuses of data, and then do useful things like predict structure, maybe design new proteins, I think make useful predictions on, so we have a paper that was trying to forecast or predict the evolution of COVID. So like how the COVID spike protein might evolve and to evade human immunity. And so I think that's like another example of the usefulness of these types of models.
What was the result of that research?
So it was kind of a conceptual. So the first research was like kind of just making the conceptual bridge between protein language models and how the underlying kind of viruses might evolve. So I think that was really interesting, and something that was really rewarding is that then we saw kind of these large like Genentech, BioNTech use the same types of frameworks to try to actually predict.
Wow.
At the end of the day, though, these are just predictions. So I think that's one thing that's like particularly interesting about working in the sciences is that you can have these like large scale models, ingest a lot of data, maybe make something like interesting or make useful predictions out of it. But at the end of the day, you have to go back to the reality of our physical kind of world of atoms and then do something, validate that it works and is useful.
Karthik, from a point of view of tabular data, obviously examples there might be things like stock prices, or if you're looking at time series data, then it's cybersecurity logs or whatever. One of the reports I read on this talked about the different use cases being things like table-based fact checking, question answering, semantic parsing, metadata prediction, content population. Like there's lots of things you can do with it. Where do you see the most promising use cases for this kind of technology outside of language or outside of words?
It's really like we're still like just figuring out. It's really hard to pinpoint one as the most promising, right? But I think a general trend is, one thing to think about these models, like Ellen was saying, right? They're trained on a lot of data, right? And just like in the biology space, when you train these models on the entire web, there are probably patterns that it picks up on that humans don't really have a good sense for. Like think of just how we search versus how Google searches, right? So I think it's really interesting to think about how you want to elicit certain kinds of behavior from these models, right? So if you talk about tabular data and you wanted to, I don't know, generate SQL queries for that seems like a good use case, right? But you could also do other things. You could perhaps ask it to, generate actions, which is, one part of our research, right? Like you can ask it to generate actions, which could be, let's say arguments to an API call, or, high level commands to a robotic controller, things like this, right? So it's really like up to you to decide how you want to massage the signals from the world into some format. If you can massage it into text and feed it in the model, you can leverage some kind of reasoning process, right? Again, we don't know for sure, the limit of these, right? And that's still like an area of active research, but you can use the fact that these models have a lot of knowledge, and you don't have to encode, or you don't have to make the model learn this knowledge, as long as you sort of provide the scaffolding around these models to sort of interface with different things, be it tabular data, stock market, cybersecurity logs, whatever.
So let's talk a little bit about what a prompt looks like for these things. Obviously, when you're putting in the input, you're putting in like a command, like, please tell me something about this table. And then you're putting in the tabular data. Here's a table to go look at. How does the system distinguish between the instructions you're giving it and the data that it's going to act on in one of these configurations?
Right. So this is where, again, like the attention mechanism helps quite a bit, right? So these models are actually like multi-layered, several hundreds of layers. They could go up to hundreds of layers deep, right? And the thing is that each of these layers has an attention mechanism, right? And if you think about how the representations are built from one layer to the other, they use this contextual information. They use like subsets of this information to build these representations. And they, as you get higher and higher, you know, you can think of more and more abstract concepts emerging, right? So in your example, I can imagine, again, this is, you know, like there's work in interpretability trying to, you know, figure out whether this is really happening, but the attention mechanism has the capability to build these representations. So if you have sort of instruction part of the prompt and then the input part of the prompt, the model can build an abstract version of the input, an abstract version of the instruction, and then apply it to figure out what to do. It is possible for the model to do that, at least.
So we have a few good questions coming in already. I'm going to ask one more to kind of set things up, and then I'm going to take a few from the Q&A that are there. If anybody has a question, put it in Q&A. You can also go upvote the questions that other people have put in, so that if everybody wants me to ask a particular question, I'll dive into that one. Let's talk about how we know whether or not it's good. As you said, Karthik, this is pretty nascent. We're trying to figure out what they're good for, what they're bad for. How do we test? Like, how do you have benchmarks for success or results here? And I can see how that could be concrete if I'm like saying, predict the stock market for me, and then I compare it to what the stock market actually did. It's pretty hard for Ellen to, you know, fire up a machine, print something with a bunch of, you know, gene sequencing tools and CRISPR and go, did I make a life form? You know, hallucination of function problems might be a bad idea. So how do we test these things? Ellen, how do you tell whether what you're putting in produces useful output, or is just, you know, is it just searching the web for stuff it's been trained on and finding it quickly, or are the model weights actually valuable?
I think it's all in the validation. And I think that's like a great question and completely unsolved. And like for any specific problem, you're going to want to design like really good metrics for that problem, right? Going back to the AlphaFold example, like one reason why this problem of protein structure prediction was so successful for the community is that, or so successful was that the community came together and created this double blind kind of challenge, which was a really nice setup for a machine learning team to come in, not really have too much domain expertise. Again, there's like a lot of domain expertise that went into designing the algorithms, but I think when you come in from like the computer science or machine learning perspective to a new area, either you spend a lot of time like kind of investing in understanding the data, understanding the domain, having, or like kind of making connections to the right domain experts so that you can make sure what you're generating is reasonable. Yeah.
And then Karthik, I guess I would ask as a final question before we take these Q&A things, similar to that, we now have non-deterministic threat models in fields like cybersecurity. People are using LLMs to generate a new virus that doesn't trigger the virus signature database of a traditional antivirus software platform because it's got some differences, so its checksum is different and so on. What are your thoughts on this sort of non-deterministic arms race? Are we going to need non-deterministic tools to fight non-deterministic threats?
In some sense, yes, right? Like, so the more different versions of the virus that you can generate, you know, we sort of need automated models that can help or at least assist with checking these kind of viruses against the database. I mean, you can sort of go for, you know, instead of exact checks, you can sort of have fuzzy checks or sort of a model trying to predict whether this could be a virus or not. But again, pretty open. I'm not too aware of the research in the cybersecurity field, but I'm pretty sure we can use models to you know, check models that actually generate viruses.
Okay, so we have a bunch of questions now, and I'm gonna go through some of them in order, and we can riff off these. Feel free to chime in with other topics if this triggers anything that you're thinking about. Shail Shah wants to know, we keep talking about power of large language models. What are good ways to validate responses and behaviors of the responses when used in enterprise so it doesn't generate things which don't make sense? So we obviously talked about this a little bit, but like, how should an enterprise start testing whether the results of its LLM experiments are useful?
I think this goes back to what Ellen was saying, right? In any domain, if you think about even in enterprise, I guess like in any vertical, you probably want to have a good understanding of the expected outputs for all the different kinds of inputs, and you want to have at least internal benchmarks that help you be confident on your use of these LLMs, because this is something the research community is trying to do and make open source, right? But that's just purely for research. But for any specific problem, I would just go and really create, even if it's an internal benchmark, create that first, because without that, you're never going to know whether you're making any improvements to the models, or you don't know how even the base model would work if you just take something like OpenAI API out of the box.
Ellen?
Yeah, I don't have any like experience on the enterprise side of things, but if I were doing that, I would personally not deploy these models in any kind of real application yet, unless there's like, lots and lots of checks. I would totally do the hacky thing and like, write down a series of like rules and stuff like that. I think we're just like in a research setting trying to understand kind of how to control these models and how to make them useful. But in an actual like enterprise setting, I think you have to be sure about what you're doing. So
are we, I mean, I must see 50 different tweets a day about groundbreaking new technologies that's revolutionizing enterprise AI with large language models. It sounds like a lot of those things are kind of getting ahead of their skis a little bit. Is that a fair characterization?
Yes.
Okay, I like short, clear answers. Sean Power, hi Sean, good friend of mine, has a question about the implications of subjective outputs. So this kind of gets what we're talking about here. When we say we want to test something, we're looking to see is the answer objectively correct. But for things like subjective stuff, a feeling or a color or a sound, there's no right or wrong. There's just like, is this output brand consistent with our ads? So what are your thoughts on the implications of differences in models whose outputs are subjective versus objective?
Yeah, I think
Ellen,
it goes
feel any better about that?
Yeah, I think it goes back to this like evaluation problem. And like something that I see right now is a lot of people are really interested in protein design. So instead of like AlphaFold is predicting like existing protein structures from the sequence information, but now if we wanted to hallucinate new proteins with novel functions, there's certainly lots of like really impactful applications in like bioengineering and therapeutics for this. And we can train a generative model of proteins. And I mean, a lot of people are figuring out how exactly to do that accurately, but when you generate new proteins, how do you evaluate it? And I think one thing coming from like the life sciences is that it's like an observational field, and you have to develop, again, the domain expertise, and you just look at the structures and you kind of subjectively evaluate it. And I think there's a lot, even though at the end of the day, you want to be objective with your benchmarks and objective with your kind of evaluation. I think there is a lot of interesting kind of, there's an art to the subjective evaluation of your results. And
literally an art,
like,
it's not a science, right?
Right. And I think there's something really nice about that. I don't know. I think it's way more kind of interesting and entertaining to do research that is, kind of blending more subjective things and more creative kinds of pursuits with like rigorous objective studies.
I'll read you this one from Jeff Renfro. Is there an accepted workflow to use of the model with a transformer-based architecture in order to match time series data, particularly data collected from a dynamic physical system? How does it compare to things like long short-term memory networks or recurrent neural networks and other methods for trying to deal with time series data?
I can answer it. Okay. Yeah. No, so there's not, I mean, I think you can think of a transformer as being quite similar in the sense like you can just feed it in the time series data and ask it to make predictions, because it does have positional embeddings. So it's not like it doesn't have some of the properties of our LSTMs or RNNs. The only thing you probably want to be careful about is like you're probably limited upfront in the maximum context that you can feed into the model. There's workarounds around that. You can use multiple levels of hierarchies and so on.
So, I mean, to make this really concrete for people who maybe don't understand this quite as much, when we talk about putting tabular data or structured data of some kind into an LLM, a comma separated value file that's like a comma, column A, comma, column B, comma, column C, is serialized, and it just has commas as delimiters, and then maybe it has carriage returns or some other characters end of row delimiters, and there's some other delimiter to show the headings. But the language model doesn't necessarily understand these things are all in the same row, or the third thing in each row sequence is part of the same column, and therefore this column header applies to it as well as it could. It understands that a little bit because it's been trained on the internet, but to wrap all of what we're talking about here is you can train it to understand the structure of that serialized data better by saying, hey, this particular value is probably part of this row of things and probably part of a column with this meaning in this unit. So I guess what I'm asking, and I'm over explaining it a little here for the sake of maybe clarity, is we're talking about changing some of the ways in which the machine learning architecture behind the scenes is set up to help it to understand tables and what things are relevant in a table better than it normally would. Is that fair?
I mean, theoretically, you don't need to do that, but you could do it.
You don't need to. So an LLM is perfectly okay at going, oh, every time I get to the fourth thing in a series of commas, I know that's part of the column called units or mileage or whatever.
Transformer can do that theoretically.
Right. But is the current like GPT-4 chatbot transformer kind of tuned for that or not?
I mean, I think you can feed it in tables like this and ask it questions. It depends on your use case and how big the table is and all of that. There are some limitations, but it's not out of its capability. But Ellen was saying something.
I was gonna say, I think it depends on how much data you have. Like, if you are in a really data-rich regime and the model can like ingest all this data and just learn the structure, but if you're in a data kind of poor regime, like in many areas of biology, then you can't, like, there's not enough data, training data for the models to understand the underlying structure. So then you have to be smarter about like how you actually design kind of the data pipelines or the underlying algorithms to take advantage of the underlying structure in the data.
Got it. Okay. So it's pretty good at things that are common on the internet already. If you're introducing a data set that it hasn't trained on in the internet, you might also need to give it information on how to extract the most important attention relationships within that data.
Mm-hmm.
All right. And I guess that's like the cusp of what both of you are working on right now, is try to understand how those models can be best optimized and validated to see if they produce useful results and so on.
Yep.
That a fair assessment? I'm just trying to get to the core of like where the cutting edge is and where the bleeding edge is in this kind of field right now.
Yeah, there's a I mean, I guess like with some of these models, there's this framework of like, I mean, it's called in context learning, but really what you're doing is like you're sort of giving it a few examples, and the model can use in its prompt, and it can use those patterns to figure out what to do. And like Ellen said, right, like, I mean, the number of examples you need really depends heavily on the type of task you're doing and the type of domain you're working with. If you have really long sequences, DNA sequences or something like that, you probably want a ton of data, and trying to fit that into a prompt might be hard if you want to use this in context learning route. And then you'd go to fine tuning these models for certain use cases and so on.
So Rupert Steffner wanted to know, when you're going beyond language, is there any, is it useful to combine LLMs with knowledge graphs?
Yeah, absolutely. I think, I mean, that's actually quite relevant to some of the stuff that we work on. So you can think of, like I said, right, like I think one of the nice parts of these models is that if you think about them as generating something beyond just text, like, just generating essays or something like that, is one use case, but you can think of it more as a tool or with some kind of an agency, right? So then you can think of anything like a knowledge graph or a database as being a store of information that you can use these models to do lots of things with, right? So as long as you retrieve some information that the models can then reason over or process, they can be quite useful. So there's a whole line of like retrieval augmented language models or retrieval augmented models that look explicitly at this problem of how do you connect models with knowledge graphs. But you can be, in general, you can probably connect them to all sorts of data sources.
I got a question here that's very specifically for Ellen. Hyder Ali asks, I'm going to say a few words I don't understand, Ellen, so you're going to have to explain these. In biomanufacturing fermentation, protein degradation processes affecting the final product quality, like frame shift, truncation, aggregation, etc. Is anyone looking into omics data and why we have these problems and how we can control intervention to make the process more efficient?
Yeah, so I think omics data means kind of like all these different kind of larger scale data, like biological data sets. Like you have transcriptomics where you measure the RNAs in all your cells, and you have like proteomics where you measure all the proteins, and genomics where you measure all the kind of DNA information. So in biomanufacturing, I mean, the short answer to this question is I don't think so, because a lot of these things are proprietary. So on the manufacturing side and on kind of the experimental side, or when you're trying to like physically make proteins, either if the people who are doing it at large scale are kind of like pharma companies or something like that, in which case all the information, like the results of the experiments, are proprietary, that's not publicly available. Or the data is just kind of like the information is just dispersed, right? It's not aggregated in any way, where it just lives in like different people's research notebooks around the world, and it's not kind of structured in a way to enable learning from that. So I think making things more efficient might be a pretty hard problem to do it without any kind of specially designed experiment to, target like your specific fermentation process. And I think that's one of the challenges for kind of machine learning applied to biological problems.
Are you hopeful that we are going to make major advances in biology with this technology, or do you feel like it's sort of unclear right now? What is your sense of how valuable the application of these learning models to biology is?
Yeah, I think in the short term, there's been so much progress in the last 5 years. I think in the short term, it's going to be extremely useful for many, lots of low-hanging fruit. Like, I think computational biology is going to be like super, like people are really interested in learning of biology, so you can do like computational tasks in this like predictive setting, like I mentioned before. But longer term, I think I'm a pessimist, actually. Like, I think there's so much that we don't understand about biology, and there's so much complexity to actually like studying it, that I don't think, like, I've thought about this really seriously, and that I don't think like AI will come in and like make some new revolutions in biological problems and understanding like how the underlying biology works. It just seems like dauntingly complex. And if I'm proven wrong, then that's great.
Karthik, what emergent behaviors of LLMs have surprised you?
I guess it depends on your definition of emergent, right? So I think what's really been interesting, especially over the last few months, is the fact that, you can get these models to do more complex reasoning, right? You can call it whatever you want, like system 2 type reasoning, but you're able to use them to, for example, like this chain of thought prompting, or these kind of think step-by-step prompting is an interesting example where, so just providing an answer, you're mimicking the reasoning process of a human doing this, right? And all of this was learned from web data. And I think that has interesting consequences, because now you can use this for many things. You can use the model to, I see a question about like, can LMs evaluate each other? Yeah, there's this idea of like self-evaluation, right? You can get an LLM to generate an answer and then ask it to sort of just reason over its answer process itself, figure out flaws, and then use that to correct its answer. So there's sort of interesting things that come up when you think of the whole process as not just input to output, right? So there's this intermediate process of, you can call it reasoning, or it also provides interpretability, right? A human can read what happened, assuming the language model actually, follows through with the process, and all sorts of things, right? It opens up things for human AI collaboration. So a lot of things, a lot of challenges that the field of AI has faced for a very long time, are coming together now, if you think of the LLMs as forming some sort of a core, right? And I think the trick here is not, again, think of them as just input to output, right? So we have some recent work which follows along this chain of thought line of work, right? We call it tree of thoughts, where you can combine it with classical AI search algorithms, and actually do much better than just like asking GPT-4 to solve a math problem, right? So it's the way you use these LLMs, there's sort of like lots of interesting directions, and I think that's been the most surprising thing for me.
Ellen, how about you?
Coming from NLP, where language model basically meant, generate the next word.
And I remember asking it, how many words are in the answer you're going to give me? And it gets completely stuck, whereas any human can go one. So there's clearly, certain things, and I love the sort of system one, system two thinking. Maybe we'll wrap up with this question, which a couple of people have mentioned in different ways, Pravin and Kaushik. They're talking about validation. Pravin points out that to validate a perspective, if you're curious and open-minded, you generally talk to multiple people. And so, as you were saying, you can have multiple LLMs sort of check up on one another, or even you can ask it several times. Kaushik points out that the validation is achievable by developing some robust validation studies, but in closed sourced LLMs, it's not clear how you can make that model obvious. And it's not trivial to fine tune or retrain an open source LLM. So you might have no recourse, and if you kind of don't have either the scope to fine tune or retrain, and you don't have insight into the black boxes. Any insights from either of you on how to validate the output of LLMs in the coming months? Where do you think that's going to go, Karthik?
I think part of it, I mean, we're going to have to develop these scaffolds, right? And, part of it can be automated at some level. I think the word for this in the AI safety community is some kind of oversight, right? So having a way to have scalable oversight is the definition of this challenge, right? And so one way to think about it is like, you can have models help with this evaluation, but you don't want to rely 100% on that, because there's recent work sort of using GPT-4 to evaluate other models and so on, right? But at the end of the day, you sort of want a hierarchy where the models help automate this evaluation process, but at the end of the day, you have to make sure whoever is a developer or whoever is using this model has to have some way of doing this. Coming to the closed source versus open source, it is a problem, right? I think we'll definitely see more capable open source models and better ways of fine-tuning. We're already seeing more efficient, cheaper ways of fine-tuning, so it should be much more possible to do this on your own. But for the closed source models, it is a question of what the companies behind the closed source models do.
So if you had to make big bets on like what are the surprising headlines you're going to see in the next 6 months applying LLMs to a field that is not just text, we can check back in 6 months and see if your bets have come true, but it's very hard to predict the future in a singularity, right? What do you think is going to be like the big headline in biology related to AI in 6 months' time, Ellen?
Probably people are going to design some new proteins that do some things, and it's going to be exciting. But I wanted to answer kind of the previous question, which was like, how am I thinking about the future of this field right now? And like the way I'm thinking about it is that there's kind of like an engineering side of things, which is how do we make these models better? And like, I'm really excited to see kind of the capabilities of like scaling up even more and just like what these models can actually do. I think it's an extremely exciting time, but that feels like an engineering challenge. Just like, how can we make this better, this technology better and more powerful? And then there's like the scientific problem of like, how do they work? And I think I had an interesting conversation recently, which was just like, what is science? Like, science is the human understanding of what's going on, in these black boxes and things like that. And so I think like there's also just like the understanding from humans of how these things work. And I think that's a really interesting kind of direction as well.
It's certainly making us question, the fundamental, what is thought? What is science? It's definitely a time for epistemic,
Yep.
renaissance in humans, right? Karthik, what do you think is going to be big news in the next 6 months or 6 months from now?
6 months is a long time, but anyway.
I mean, you probably couldn't predict where we are now from that GPT paper. So,
yeah. I think we'll probably see, right now it looks like open source smaller models are not as capable as something like GPT-4. I think we will see more capable smaller models, and likely source of that would be the training data. That's my prediction. Like, it's not just about the number of parameters in the model, but also the how you train the model.
Yeah, I've seen a lot of people talking about in the same way that Neo just says, I need guns, or I need to know how to fly a helicopter or do kung fu or whatever, just gets plugged in and downloaded, that we're going to see these sort of ready-made models, particularly as AI models get trained on stuff that AI generated and kind of self-pollute, that we're going to see a whole bunch more information around, do I have a trusted repository of data that I'm licensing from someone to feed in a structured way? It seems like, those modules are going to become an increasing commodity.
Yeah.
Awesome. This was a lot of stuff to cover, and I think there's a huge range of understanding from people. Some people really get this stuff, and some of what we said is probably like, yeah, I know that. Other people, concepts like temperature and attention are relatively new. So I want to thank both of you for adjusting the altitude of the conversation. But clearly this is much more than just predicting text, and it's going to have widespread implications. Ravi, back to you.
Thank you. It's been an amazing conversation. I want to thank you, Ellen and Karthik, for coming down and chatting with us from Princeton, and Alistair, as always, for incredibly stimulating kind of and provocative sort of moderation. So thank you all. Olivia?
Yeah, thank you so much, Ellen, Karthik, Alistair, for this intriguing panel discussion. And then just for our audience, I did go ahead and link the meetup page in the chat box, so make sure to sign up for all of our upcoming events. And then we'll go ahead and wrap it up here. And thank you everyone so much for joining.
Thank you all.
Thanks for having us.
Bye-bye.
Thanks for having
Thank
us.
you, everyone.